Hey everyone, hope everything is going well with you guys. Everything is going well with me so far. I just keep cranking out video after video and getting us further and further down the road. Today we're going to learn lesson 6.4, which is the definite integral as a limit of the sum. Now this lesson is going to come in two parts. I'm going to do part one, and then I'm going to do part one right now, and I'm going to do part one's homework, and then I'm going to do part two, which is a little bit trickier and a little more in depth, and then I'm going to do part two's homework down the road. So we're gonna bite this off one piece at a time, okay? And then we're looking at 6.5 review and chapter 6 worksheet for test. This is all on the horizon a ways yet. So the first chunk of this lesson is really set up for the second chunk of this lesson and the next lesson. So a lot of the things I'm going to talk about, I want you to take really good notes on, but this isn't actually what you're going to be doing today. The actual assignment today will just be more practice on definite integrals and finding values from certain points to another point. So the actual homework from this part of today's lesson should be very straightforward. But this discussion I'm going to have with you right now is going to set you up for the part two of this lesson, and more importantly, it's going to set you up for lesson 5, which is heavily based in this concept, which is the definite integral is the limit of the sum. So if we rewind definite integrals back to their beginning, when Newton and Leibniz were first looking at definite integrals, Newton was looking at it as a way to get from derivatives back to original functions. But Leibniz came at it from a completely different direction, and he was trying to find area under the curve. And he successfully did so using limitation. And the work that he connected it to was work done by a guy named Riemann, and they call them Riemann sums. And what they are is they take a area under a curve and they split it into regions, and then they shrink the regions and they limit them together. And so here's what I'm talking about. So originally, Riemann would have said, if I want to find the area of the region under this curve, what I could do is I could take the curve and I could split it into rectangles that represent the area of each chunk of the curve. Now, the rectangle can either have a height that hits the curve on the left side, or it can have a height that hits the curve on the right side. So I'm going to do all left side rectangles, but you could do all right side rectangles if you want to. It makes very little difference. So if I go up the left side until I hit the curve, cut my rectangle straight across, and then drop it down to my hash mark. Now I have a rectangle that has a width of 1 and a height of this value on my curve, whatever that might be. Now my next rectangle does the same thing. It shoots up this hash mark until it hits the curve. It comes straight across until I'm right above the next hash mark, and then goes down. So now this rectangle has an area, has a width of 1 and a height of this corner of my rectangle, which is that value on the curve, the value of the curve at 1, the y value of the curve at 1. And now I fire up another rectangle, hits the curve right there, shoots across, and drops back down to there. And then I shoot it up, hit the curve, drop it straight across, back down to there. And then I shoot the next one up, drop it straight across, and down. And then, if I take the area of each of these rectangles, knowing their y value based on what the y values of the curve are. So what I would do is, whatever my curve is, y equals yada 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 yada, I would make a table. I would need the values at 1, 2, 3, 4. I need them at 0. 0, 1, 2, 3, 4. 0, 1, 2, 3, 4. Then whatever they are here, I'm going to take my width of my rectangles, which are all 1s, times by the height of the rectangles, which are all the y values, and then I add them all up and I get a estimate for the area of that curve. Now, as you can tell, the curve has some space that it is missing and some space that it has gained over that chunk of zone. So this space is space under the curve that we've lost. This space is space under the curve that we've lost. However, this space is space under the curve that we gained. This space is space under the curve that we gained. This space is space under the curve that we lost. And this space is space under the curve that we lost. So we have some loss and some gain in our curve in between these zones. So then Riemann said, well, what if I want a better estimator than this? Because this is not doing a perfect job. I'm not getting the best area I can possibly get. So he said, what if I take the same curve, and I'll get it as close as I can here. What if I take that same curve and this time, instead of breaking it into 5 sections, because it's from 0 to 5, because my units are from 0 to 5, but this time I break it into 10 segments, making each rectangle I create only half a unit wide. Now what happens? I'm still going to have this rectangle here, only it's going to be half as big. And then the next one shoots up from that point, only it's half as big. And the next one shoots up from that point, and it's half as big. And the next one shoots up from that point, but it's half as big. And then the next one shoots up from that point, and it's half as big. And what you end up with here, this time, is 10 little rectangles. And you'll find that we still have space. We still have some space that we are over. We're over here, we're over here, we're over here, we're a little over there, we should be right on there, should be right on there. But you're also under here, and you're losing a bit there, you're losing just a tiny bit there, you're losing just a tiny bit here, and here, and here, and here. So what you see is my little red zones and my little green zones, compared to my little red zones and little green zones up here, are significantly smaller. So this new application of area has become a much better estimate of the area under the curve than my original. So if I go through and I add up the area of all these rectangles, which are 0.5 wide and then however tall, so delta y, delta y, delta y, delta y, tall, okay? And I add them all up, I'm gonna get a much closer representation to the area of this curve than if I use this picture. And the smaller I make my rectangles, if I shrink them down to a third wide, or a quarter of a unit wide, or an eighth of a unit wide, or a 16th of a unit wide, the smaller I make my rectangles, the closer to the actual area I get, giving me an opportunity to move this whole process into calculus. And so what Newton and Leibniz were able to do at this point in time was say, what if we shrunk the rectangles down to basically lines? Just like when we were doing our secant lines and we sucked them in until they were tangent lines. What if we shrunk these rectangles down so that basically every rectangle was just a line? And I filled this zone with tiny little lines. If I did that, and I added up the area of all the little lines, I would be able to get a solid estimate of this region. And so what that tells us is that the sum of all of these little rectangles, and they would say the sum of our delta x times our y1 dot 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 y n is equivalent to the integral from whatever zone. So if we go from A to B, here, then we'll go from A to B here of whatever our function is, f(x). So basically, the whole premise of this is if we cut these into tiny little zones, we would be able to use an integral to find the area. And so that's what we're going to turn around and do. Now, in part B of this lesson, we're going to move that forward even another leap into looking at three-dimensional figures. And then in lesson 5, we're actually going to put this application to work doing some Riemann sums using the trapezoidal rule and the Simpson's rule, which are two ways of doing these Riemann sums. So keep this in mind. This is coming back in a later lesson. For now, what we're going to be doing is integrals through certain regions. But ultimately, we are going to come back and do exactly this. So make sure you've got this good notes on this set up in your notes. Okay? Now, we're going to do just one example because I only want to do the first chunk of this for this first homework assignment, and then we're going to do just the second chunk for the second homework assignment next week. So this week you're getting this piece in notes and doing this homework connected to this piece, and then next week you're going to do the next piece and the homework connected to the next piece. Now I may be ramping that up just a little bit as we move forward, so just be ready for that, just in case. I may be pushing out additional material if I feel like you guys are really okay doing this. I'm trying to be really open-minded and back off a lot to give you ample time to be able to work through some of this. But if I feel like we're doing okay and I can push you a little bit harder, I do have a chunk of material I'd still like to get done. Now, I'm not gonna go crazy. I mean, you know, you're not gonna get lessons every day or anything, nutso like that. But I would like to crank it up a little bit faster than a lesson a week, which is kind of dragging along right now. But, a lot of that is gonna depend on how I think, you guys are doing. If you take a look at example 4.1 in your book, which happens to be on page 395. Example 4.1 will be almost exactly like most of the homework problems that I'm going to be asking you to do. They're all directly tied to our compound continuous interest formula. So just a reminder of what that looks like. T equals P e to the RT, where P is our principal, R is our rate, and T is time, almost always in years. Time to get a little sloppy on there. They're on me. Okay? So now what the example says is, money is transferred continuously into an account at a rate of $1,200 per year. The account earns interest at an annual rate of 8%, compounded continuously. How much will be in the account at the end of 2 years? Now, the issue that we occur on this is before, when we were doing problems like this, we had to do them in multiple parts. We had to say, okay, this is year 1 and this is year 2. Now, we don't need to do that if we use our compound continuous formula and we go ahead and we use integrals to find that entire region. So, I mean, we can do this. We can get the interest and the growth in place by just using our formula and taking its integral now. So we're going to do the integral from 0 to 2 because we want to cover the first 2 years of principal, which is 1,200, e to the rate, which is 0.08 t. Now you can use x up there if you want to. It really doesn't make any difference at all. Okay. So now we take this integral. Now the integral of that gives us a region from 0 to 2 of 1,200 e to the 0.08 t, but then you divide this by the derivative of the top, which happens to be 0.08. Which takes us to the region from 0 to 2 of 15,000 e to the 0.08 t. Now all I have to do is kick in my 0 and my 2. Remember that when we're dealing with e's or ln's or some sort of, it would be integration by parts or some sort of parenthesis situation where we're doing a complex integral with either a denominator or parenthesis, then we have to actually plug 0 in. We're not doing just a standard integral, so 0 is going to give me a value. And in this case, when I do anything to the 0 power, I get 1, and then 1 will times to that 15,000 to become 15,000. So I'm going to take what I get when I plug in 2, and I'm going to subtract what I get when I plugged in 0, which is 15,000. When I plug in 2, I get $17,602.66. Making my total value of my investment $2,602.66. This problem here is very close to a lot of the problems that you'll be asked to do in the homework. So when you hop out and you grab the homework video from this, you'll find me working out the first couple of homework problems, and then you'll be able to go ahead and kick through the homework here.